In this video we're going to take a look at the back computer challenge on HackTheBox. So this is an easy Pwn challenge and the description says it's your time to save the world. So let's start by downloading the files and testing this out locally. This challenge is a bit of a step up, by the way, from the last two Pwn challenges. So if you haven't checked them already, I recommend watching the Reg and Jeeves challenge before moving on to this back computer challenge. But it's up to yourselves. Let's start by doing some basic file checks. So let's check the file type first of all. See that the file type's another 64-bit LSB executable for Linux, and it's stripped in this case. So if we run strings-n10 back computer, we're not going to see all of our usual functions here because the symbols have basically been stripped. And that can make debugging a bit more difficult and reverse engineering in some cases, although it won't be too difficult. We'll see that shortly. So let's have a look at these strings first of all. What do we have? It's going to give us an idea what's happening with the program. It's giving us a couple of options to track or chase Joker, and then it's either going to give us print out a pointer to a location, memory location, or it's going to ask for a password, and it looks like this is our password right here. And if we get the password wrong, it's going to say it can't give us access, otherwise it's going to say access granted, and then it's going to take some navigation commands and then either roger that or too bad. Okay, so even without running the program, we can get a good idea what's going on. Let's have a look at the security that's set on this as well. Back computer. Okay, so no canaries. NX is disabled, so unlike the previous challenges, if we're able to get some shellcode placed on the stack, we will be allowed to execute it. And pi is enabled, so this is going to mean this can cause some problems in terms of the addressing as well. Let's actually go and have a quick look at we'll search Checksec explained. It's a slight detour, but it's worth taking a look at. High-level explanation of some binary executable security, and this link I'll put this link in the description. Then this link will describe some of the different protections. So the stack canaries we'll probably be dealing with on some challenges shortly. If you go back to the ROP Emporium series that are released, there was a challenge for bad characters where we had to avoid bad characters. So kind of similar. Basically, there'll be values on the stack that cannot be overwritten, so we need to in some cases find out what those values are, and then we need to overwrite those with the correct value so as not to trip the canary. No execute means that we won't be able to execute code in the stacks. That its data is either readable or writable or executable. So in our previous challenges we weren't able to do that. In this challenge we are, so it's a good indication that we'll probably be trying to inject some code onto the stack for execution. And then finally, pi, as we have here, position independent executable, basically means that the program and its libraries will be loaded at different addresses. The addresses can't necessarily be predicted. And it also means then if we run, whenever we go to, say if we open this in PwnDbg and GDB and try to disassemble, we won't be able to get the addresses of the instructions and the functions and things like that. We'll only be able to get the offset because we don't know where it's going to load in memory, essentially. So this is something that we'll need to take into consideration. I'll mention this again later. So we're going to want to open this up in Ghidra soon and go and see if we can decompile the code and get a good look at it. But let's just run the program first. Let's make it executable. Try and run it. We have the option track Joker. We'll hit 1. You see if we keep hitting 1 there, we get the same result. Let's try and run the program a couple of times. You see that we're just getting a different result for this each time each time we run the program. If we do 2, it asks us for a password. ABC, okay, wrong password. But if we run this with ltrace, and we saw anyway with the strings, but if we run with ltrace and go chase Joker, what's the password, ABC, we'll see here string compare ABC with bat password. No, that doesn't match. So let's try that again. Let's do 2. Let's paste that in. And we get access granted. Enter navigation commands. Say hello. And it says roger that. And then, so it reads that in, it puts roger that, and then returns us back to the main menu. And then we can exit the main menu by using a different key, any key that's not 1 or 2. So that's basically how the program works. Let's open this up in Ghidra and take a look at it. Alright, so we'll open up Ghidra, create a new project. It's really annoying that you can't just open a file from Ghidra from the command line. Or I'm pretty sure you can't go without creating a project. If you can, let me know. Alright, let's just create this back computer project. We'll import our file, back computer, okay, and then double click it. We'll do all the default options there on the analysis. And we have a couple of options here then, so you can see that no functions come up here. Unlike the previous examples we went through, there is no main function here because this has been compiled, but it was stripped, so you just have these randomly named functions. So you could go through and manually have a look at each function. You could also have a look here for the entry, and then you can go to the entry and have a look at the functions that are called here. If we go into these, let's go back. This is basically what's going to be called, so this is essentially our main function here. Something else we could have done would have been just to, let's go back to where we were, to search for the strings. Another easy option. Search for the strings, we see this like bat password, all this sort of stuff. So there we go, we can just select that. We can see the string and then see where was it referenced, this function. So we just double click that, it takes us to the function, and now we can have a look at our code. You will also see that the addresses here, unlike the last 2 challenges that we went through, the addresses here aren't like valid memory addresses. This is an offset to where the base of the binary will be because that pi was enabled. So we can use these addresses anyway in terms of debugging and setting breakpoints and things like that later, or calculating offsets to things if we needed to add stuff to our exploit code as well. But let's see what's going on in this function, our main method. So we have 2 while loops running continuously here. At the top we had these stack variables declared, a char of 16, and then one of 76 bytes as well, undefined. We have a memset operation here with the 16 character stack, and then this is the behavior that we observed whenever we ran it. It asked us, where do you want to travel? It gives us, if we press 1, it gives us the pointer location to the stack 84, which is right here, the 76 byte stack. And that's the address that we're seeing coming up, is the location of this stack. So then whenever we go out of that, we have the option to press 2. We press 2 and it asks us for the password, and then we have to enter this password as we did. If the password is not right, it will just print here and exit. Otherwise it will grant us access, and it asks us for a command. At this point it takes the data that we give, and we can see here that we have it takes 89, which we can go here and we can convert as well. You can see that that is 137 in decimal. So it takes 137, but we know that up here this is actually 76 in decimal, so there's a buffer overflow there, potential buffer overflow, and it reads it into the stack, which is the stack that we get the location of as well. We're given the memory address of this location, and that's that. So essentially the idea here is going to be, because because the location of the stack is going to change each time, whenever the program runs, we need to extract this address, and then we need to enter in a password and enter in our shellcode, essentially some shellcode that we want to execute as our commands, and that is going to be stored at the stack location, which we have the address of. So then we need to overwrite the return address, the instruction pointer. We need to overwrite that with the address of this stack where we've placed our shellcode. So we grab the address here, we inject our shellcode here, and overflow the return address with the address of our shellcode, where this is being read to. Hopefully that makes sense. So we've identified what we need to do statically. Let's go and try and do some of this stuff in GDB before we go into Pwntools, but it's going to be a lot easier to do most of this in Pwntools, because in GDB, if we keep, every time we want to run it, we're going to have to like grab the address, copy the address, and enter the password, and then overflow the buffer. But we're going to identify the offset and stuff manually, and then we'll move into Pwntools. So we'll open this in GDB PwnDbg, or Jeff, or Peda, or whatever plugin you're using for it. And I always say this, but just in case you haven't caught any of the previous videos, if you're using PwnDbg, you can type PwnDbg here, hit enter, and it'll give you a list of plugins and functions that you can run from here. You can quickly grab ROP gadgets, for example, use Ropper, without needing to go back. We can also type help and pick something, help data, and drill down to find whatever like kind of documentation we need. So if we open this up, we do info functions, and we don't get a list of usual functions because the symbols have been stripped, so we can't see the main function stuff here, although Ghidra has determined that sort of stuff. Well, it didn't name it, but it did have these functions here available to us. Similarly, the addresses, because of the pi, you can see that these are just offset addresses, which are going to be the offsets of whenever it's which will add on whenever the program's in memory. So if we run and even just stop it straight away and then try and do info functions again, it's going to get all the functions that were loaded. It's going to actually resolve these addresses as well. Let me close that and run it again. We can also open up Radar with R2 from here, do AA to analyze all flags, and this will find the functions. If we do AFL, get the list of functions here, and we get the offsets, so we could use this to set up breakpoints and stuff to main. We can disassemble these as well. We can do smain and then PDF, disassemble, and if there's somewhere particularly that we want to then set breakpoints later, or if there's something that we want to access in our exploit, we'll be able to grab offsets using this. Let's close that, let's go back, and let's try this out and see if we can get our the offset to the instruction point that we want to overwrite. So let's generate our cyclic pattern. We'll say cyclic 100, grab that, and let's run the program. We don't need to track Joker yet. Let's just go to chase. Oh, we need to enter the password. Luckily I still have it here on the screen from disassembling in Radar, otherwise you can just go and grab the strings in another terminal or something. We'll enter the password, and now we want to enter this cyclic string. Paste that in. Now notice that it didn't crash because we still need to return. It's not going to crash until we return, so we can just put in another value here, and we now can see that it's crashed. We can see that obviously, or not obviously, but the cyclic pattern is filled up the registers. It hasn't gone into the RIP because this is an invalid address, but these are the bytes that would have made it into the RIP. So we just take the first 4 bytes from the RSP and do cyclic -L to look up the offset, and we'll find that it was 84 bytes in. So we need to write 84 bytes, and then we need to write the return address, and the address we want to return to is going to be this address of the stack. So we'll run the program, we'll track Joker and extract the address, and then we'll go back through the program, enter the password, and then we'll give our shellcode that we want to execute, which will be stored here. And we then need to make sure that we write our 84 bytes total before we overwrite with the return address, which we grabbed from here, which is going to be the location of our shellcode. That'll make more sense as we go through it, but that's how we could grab this manually. As you can see, it's kind of a bit annoying because you're going to have to go through, and if we could go through this and try this with like capital A's and B's and things like that to make this look a bit to make it easier to see on the stack and kind of go through it, but it's just because you have to keep entering the password, and then you're gonna have to copy and paste the address, you're gonna have to copy and paste the password, and you have to copy and paste your it's just it's gonna be quite a slow process. So the better thing for us really is to move over to Pwntools and start to automate this as soon as we can. Okay, so the offset's 84 anyway. Let's go over and grab the Pwntools template. I modified it slightly. Let me copy it here to I'm just going to call it exploit.py for now because I don't want to name it the same thing as a binary and just make it harder to autocomplete. So we'll copy that here, we'll open that up with Codium, and let me just go through the couple of changes that I made to it. So I can't remember if I made this in the last video. I'd already made this in the last video, but I've changed these just to use a PC and or SP variable registers, which are just generic, so it'll use EIP or RIP depending on what architectures is set, rather than you having to go and change this each time. The only thing you will need to change is still this bit here. So if you're dealing with 64-bit, just uncomment this and comment out the 32-bit, and we should be able to use that as a quite generic thing. Obviously we'll need to modify our code and stuff here to do this, but so we'll do this in a second. But the other changes I made were adding this from the like template to so that we can run the program locally, or we can pass in if we pass in Python exploit, it's just going to run locally. If we pass in Python exploit remote and then a server address, obviously typed incorrectly, and a port number, that's going to run remotely. And if we want to run with GDB, we can just do GDB, and we can do no ASLR to turn ASLR off there, as you can see here. Debug no ASLR. So the GDB script is set down here, and it automatically initializes PwnDbg and then continues. So you just want to go here and set something to say break at whatever address, or break main or something like that. Put whatever you need in there for your script, and that's essentially it. It still does all this stuff the same. Change this between info and debug whenever you're whenever you're having problems and need to see what's going on behind the scenes. Put the address of your binary in here, and then this will find the context, so that throughout our exploit we won't need to worry about what operating system, what architecture, what bits, whether it's LSB and things like that. And I think that's everything. So let's go and try and start putting this together for the back computer binary. So first things first, let's update this so that we can get the location of the EIP straight away or automatically. We already know from doing it here that it's 84 bytes in, so we could just go down here. We could just be saying the offset is 84, but we want to try and automate it, so let's do that. So I'm going to comment this out for now. Let's just work on getting the offset, and once we've got the offset, we'll go and start building up our payload. Whenever it runs, it's send line after. Let's see what happens whenever let's just do this step by step. So If we run back computer, it says welcome to back computer, and this is the last thing it says it comes up with. So we've actually got that already in place. And what would you like to do? The first thing we want to do is, we don't need to track Joker yet because we're going to do that later. Right now we just want to find out how many bytes do we need here. So we're going to say 2 first. We're going to give the answer of 2 first of all, and then it's going to ask us for a password. So oops, it's going to ask us for a password here. So after it says that, we want to send in the password, which is, let's go and grab it. I'll just do strings. Grab the password there. Okay. Make sure it's all formatted properly. Alright, so we enter in the password. And then let's go and do that here. We enter the password, it comes up access granted, and then enter navigation commands. So let me first of all just grab this. It's gonna ask us for the navigation commands. So after it asks us for that is when we want to send our cyclic payload. So now we're gonna do the payload. Okay, so we do that. The other thing was, after we do that and we give it our, let me go back again, enter navigation commands. If we go back here and give it this 100 byte cyclic payload like we're about to in Pwntools, it doesn't actually crash the program. So in order to crash the program, we need to make it return, so give it an invalid value, and now we get our segmentation fault. So we just need to also go back and do this send line after again, and provide it an invalid value. Now if we run this, let's try it out. Python exploit. Oh, we didn't put in a binary name, which is bat computer. Let's try that. And there we get our offset is located at 84. So now that we've got that out of the way, we can move on to our actual exploit. Right, so let's do stuff one step at a time here before worrying about our payload and anything else. I'm going to remove this whole write payload thing. It's really not much point here because we can't just pass the payload in anyway. You know, it has to be done through a script really that's going to automate putting in the password and stuff like that. So it's not very much point in being there for this challenge. So let's start off. Let's go back and see what we need to do again. Let's run back computer. It asks us to track Joker, so that's what we need to do. We need to grab this address. So we can say grab our send line from here, change it to IO. Don't really need to copy and paste that. And we're going to send 1 because we want to track Joker. And we need to extract the address. What I'm going to do is go to my GitHub and go to the ROP Emporium series that I did a little while ago, to the pivot challenge, because I remember specifically writing some regex to do this. Here we go. Get the pivot address. It's for 64-bit as well. So go put that here, and in this case it's going to be our leaked stack address. We'll just call it stack address. Okay, so this is going to take, it's going to receive as a string the response to this, as we have right here. It's going to receive that as a string, and it's going to use regex. Have I got RE imported here? Make sure we've got RE imported. It's going to use regex to extract that value, and then it's going to convert it to base 16 int, so that if now we go here and say, in fact, let me go back to the GitHub. Let's make things easy. pivot address. And let's try and run that. We get that there was no group there for this one. Let's have a look and see what it's actually receiving. Let's comment this out and say print that out. It's getting nothing, that's why it's not finding anything. Okay, let's see what else we have here. Receive lines, and we need to do receive, it needs to be received as a string. Let's try that. Ooh. Receive line, maybe? There we go. Okay, so there's our address. So let's just go and change this to receive line s. Let's run that again. And there we get our stack address is printed out as the as it should. So there's our first stage. We've got the address that we're going to need to leak. Or should I say we've leaked the address that we're going to need to use. So if we were building a payload now, essentially what we'd be saying is we've got our offset, it's 84 bytes, and at 84 bytes we want to insert the stack address. This payload, this flat, is going to use our context up here to basically pack everything, so that'll all work for us, no problem. If we were doing this outside of this, we'd need to make sure that we use pack, or if you don't have the context set, you'd need to specifically say whether it's the pack 32-bit, pack 64-bit. We don't need to worry about that, so we either need to just use pack, or if we're using flat, we don't need to worry about that at all. Okay, and so what will happen if we do this? Well, at the moment, nothing, because actually we need to also do this again. We can copy all of this. Alright, so we can build up our payload. We can copy this, change this to IO. Not IO error. Change that to IO. And that's going to enter the password. And then we're going to get down to this. Yeah, we can just copy all of this. Okay, and we're going to send this payload. And this payload is going to say, just write 84 bytes of a cyclic pattern, and then write the address that was leaked here. And then it's going to overflow the buffer, those 84 bytes, and the return address that we've injected is going to be executed. That's what we're going to return to. But all that's going to do is return to the beginning of our offset, so it's just going to return to our cyclic pattern. So we can go and have a look at that and see what it looks like. Let's try and run that. Oh, we need to change these to IO. Okay, so let's run that again, and we're not seeing much. Let's go and put this on debug. Run through that, and we can go through and trace exactly what's happening. So this is just what's happening at the beginning. It's finding our offset here. It comes back and then says, okay, here's your offset. It's right here at 84 bytes. And then we're going through the actual exploit where we say, okay, the option we give here is 1, and it comes back with the address. We extract the address, and we've printed it here, and then we send 2, and then send in our password, and then it comes back and asks for the navigation commands, and we send this padding, which is our 84 bytes of padding, which we've extracted our offset right here. So we have 84 bytes of the padding, followed by the address where was the address? Here's the address right here. So you see there's the B4 E5 20, bearing in mind the difference, the reverse order because of the little endian format. So you can do it the other way around. 7F right here, FF right there, 0D right there, and that's essentially what's going to happen. So what's going to happen at that point is, well, we could let's see if we can have a look at this with a debugger. We have GDB here. Let's set this to break. So let's go and run this again, and this time we'll do Python exploit GDB no ASLR, and whenever we run that, it's gonna stop. We have that breakpoint set up, so let's move this over here. This is our debug window from Pwntools. You can see it hasn't got down to this stage yet because we've got this breakpoint set up. But if we go to our debug window and try to disassemble, we're not going to be able to do that. We're not going to be able to get a main function. If we get a list of functions, you can see here, yeah, we're not able to. So what we can do is we can say, let's do piebase, and it'll tell us the base of the binary, the base of back computer, and we can, let's do piebase-h for help, and we can pass it an offset. So if we go to our Ghidra, we can find out what the offsets here are of different instructions or different functions. We can also do that in a variety of other tools. So let's actually open up Radar and we'll do R2 back computer, AA, AFL, and then we could be passing in one of these functions. So for example, let's grab the main function and let's say piebase and pass that in, and it'll actually give us the address of the main function. So we can then say, okay, we want to break at the main function, and then whenever we continue, it'll stop whenever it gets there. Something else we can do even better than that is we can say break RVA. Let me do break RVA help, and it'll break at an RVA, a virtual address from the piebase. So we can do the same thing and give it an offset. Let's actually go into our main function here. Let's do s main PDF, and if there was somewhere here specifically we wanted to break, let's say we wanted to break here just before the function returns, we can copy that address. We can say here break RVA and paste that in, and that will set that breakpoint automatically for us. And what's really cool as well is we can also just go and put that into Pwntools. Now that I updated the template script, you can just go and set your GDB script to whenever, as soon as the program runs, it's going to do break RVA, and it'll break there on its own. So with that done, we can go back. Let's go back to the window here and just hit continue. We can see we've hit our first breakpoint, and we can hit Control and C to go into our stack. And let's actually go back to our debug window. So there's nothing too much that's happened here yet in the debug window. Let's go back, and from here we could be having a look at addresses, but it's not actually given us the address yet of the leaked function which it was looking to see. Let's continue, and oh, it looks like it exited there. If we do x over 50x, yeah, okay, it exited. Okay, let's go back and finish off working on the exploit. We'll be able to do some more debugging later, but at the moment we know what we need to do. We're overflowing the pointer, the return address, with the address of our essentially at the moment of our padding on the stack. So instead of this padding, why don't we try and put in some code to execute, so that whenever we return to that address, it's just going to start executing our shellcode, because we have that NX disabled, as you can see here. So we will be able to execute code if we place it in here and jump to it. So let's clear this. Let's go back and work on that. Let's close Radar down. Let's go back to our code. And okay, what do we want to happen at the end of this as well? Let's run that. Let's run that again without the debug. Okay, we're sending that. Let's, after that's sent, let's do print io dot receive all. Let's do receive. Okay, it's not receiving anything after that. Let's go back and let's start to work on a shellcode here. So we can use shellcraft. Let's start our shellcode. Let's say shellcode equals shellcraft, and unfortunately I can't get autocomplete to work for this with Linux. Sorry, with Codium or VS Code. So let's go to Pwntools shellcraft and have a look at the documentation. You can have a look at the docs here and see the different kind of functions you can use, but essentially we could access shellcraft AMD, let's say sh, oh god. So we could access AMD 64 linux.sh. For us, we've already defined the context up here, so it already knows we want 64-bit. Actually, it already knows we want Linux as well, so it should probably work just with doing shellcraft.sh. I've not actually tried that before. I normally would still go do Linux, but it does know what the operating system is, so it should. I'm going to try that. I'll try that now. And that's basically going to generate our shell. Let's go back to the docs here and see execute a different process, and we see that it just calls shellcraft.linux.sh, and that's going to deal with everything behind the scenes for us. We could use other things though as well. Let's go to, I'll put a link to this in the description. Let's go to the command line, and we can just run shellcraft here. Shellcraft, let me do shellcraft-h. Oh, usage pwn. Okay, pwn-h. So you can hex encodes data. Okay, there's quite a lot you can do from here. Let's do shellcraft again. Okay, shellcraft list. Okay, shellcraft-list. Okay, so this gives you the list. So if you do shellcraft-list and then grep Linux, then we'll get a list of things that we could be calling here. So another thing that we could just do is say, let's just grab cat. I'll create a flag.txt here. Let's create this and do flag, fake flag, save that there. Oh. That's weird. I opened it as flag.txt. It should have just saved right there. Okay, yeah. So that's fine. So there's two different things we can try. Let's actually comment this one out for now, and let's start by saying shellcode equals shellcraft. I'll put Linux just for now and cat because I'm not too sure if it does. And we want to cat flag.txt. Which all looks good. We also want to compile this, so let's actually, yeah, well, I'll just do it right here, ASM, and we can see here it takes in the shellcode and it's going to assemble it into bytes. So if we do this here, and I'll just run this again with the debug on, it should show us some of the behind the scenes stuff. You can see here it's assembling this code, this shell code, and this is what we'll be using then in our as our payload. So instead of saying that offset there, let's change this up slightly. I'm going to pass in an array here instead, and let me change that. Pass in an array here instead. We know that we're going to want to give it the stack address. That's where we're going to be overflowing to, or that's where we want to return to, and there are that's going to be the beginning of this payload. So the beginning of this payload, then we want our padding and our shellcode. So, well, we want our shellcode, but we also need to make sure that our shellcode is long enough that we still overflow the return address with this stack address here. So we need to make sure that that's padded out as well. So what we can do is say this is our shellcode right here, and then for our padding, let's say padding is equal to, and we could just give it some characters here. I'm going to give it some no operation instructions, some nops, just because it's nice and safe anyway. It's not going to risk any bad characters going anywhere on a stack. And let's say we want to, how many nops do we want? Well, we want offset, which was 84, but we want to subtract the length of our shellcode from it, because we're also going to be concatenating that in there as well. Hopefully that makes sense. And then we can do our padding, and we can do our shellcode. We could probably do them the other way round as well, but I think that's fine. This is all going to be packed down based on our context that's set up here, our architecture and stuff like that. And I think that's looking good. Let's try and run that. So we can see our shellcode here that did go in there. We have our no operation instructions, which are 90. And then we have our shellcode here. We can actually see in the text bit there we have the flag.txt. It's being called. There's no new output here. Let me go back here. Receive lines. Do we get anything? Okay, too bad. Now he's going to save Gotham Alfred. Let's go back here and say we're going to receive until, and we want to receive until I'll paste in. We don't need the whole thing. All we need is the end of that. But I like to paste in the whole thing just so that when looking at the code, it's easy to compare it to the I need to, because there's a single quote in this, we need to put double quotes or escape the quote. But yeah, because it's just easy to compare it to the program there. If you only use like the last word, then when reading through this script, it's not as easy to see what's going on. Okay, so we'll do that, and then hopefully afterwards it should retrieve our flag. If it doesn't, we'll do some debugging, but let's put that in anyway. So yeah, it's now receiving that. It's just getting to end of file, so it's not receiving our flag after that. So there's something wrong here that we need to identify. What I'm going to do, just to demonstrate, because we modified our, we set this GDB script up. We're using GDB debug here instead of the GDB attach that we've used in the last couple of videos. Let me set up the GDB attach and just demonstrate something that we could do using that. Okay, so I just copy and paste this from one of the last videos where we had this set up to GDB attach and init PwnDbg. What we can do here then is, let's break this off and say we want to set a breakpoint, so we'll still need the B star here, break star, and then we want to break at our stack address, which we'll need to put in hex, I guess. Let me quickly print that. Stack address, yes, okay. So right here, that looks like it's the right format for GDB, so we can just go ahead and say copy that. We'll uncomment the script and paste this in here. And this should then set a breakpoint at this stack address, so that once everything's finished executing, it sends off a payload, it sends the 420, which is going to cause it to crash, and it's going to jump to our stack address, which is going to be right here, the beginning of this padding. And as it jumps here, that's when the breakpoint's going to kick in, and then we should be able to analyze what's going on. Let's try that. Close some of this down, clear the way. Okay, so we'll just run Python exploit now, and the GDB attach will run for us, so we can move to the right here. This is our Pwntools debug info, and then on the left we have our GDB debug. And we can see it set this breakpoint up. We can go and compare that right here. You can see it's the GDB script, so it correctly extracted this stack address and set up a breakpoint there for us, and that's due to this code here. So that's not that code, sorry. That's due to this code right here. So this is another way you could do it, rather than using the GDB script and setting breakpoints using the pi offsets. We can maybe grab the leaked address as well. The only thing is, if you want to break like just before it jumps to that address, then we'll be better off using the piebase stuff in here instead. Down here you can see we have our shellcode. This is what's going to be sent. So we have our no operation instructions, we have the cat flag.txt, and you can see the flag.txt string in here. And then at the end of that 84 bytes in, we have our address, the address of the leaked stack address here. So 7FFF, you can see over here, 7FFF, BA8E42, you can see here, BA8E42, A4. So it's just in reverse format, but we can see it's the same address that we have here. And what we could do is we could grab that address as well and say, let's have a look at what's in there at the moment. Why don't you get do x over 50x, and we can see these in hex. And this hasn't, we've set the breakpoint, so this hasn't been executed yet. We're just waiting for this to occur. So well, sorry, we're waiting. This is being sent, but we're waiting. We need to wait until, if we remember, let me go back to the code here. We need to wait until we return before that's actually going to be executed. So it's not being injected here yet. So if we go now, let's do next instruction. Or well, we have the breakpoint set to go to there. So let's do continue. We can see here now, if we go, let's do the same thing again, x over 50x, and you can see now we have our no op instructions in here, the 90s, followed by our 6a value, which is right here, again reverse order. So look at it, it's a little bit harder to track because of the reverse order, but we have the same values that we have in there. Let's see, this was our address that we were jumping to, the 7F, which is 7F. The address that's here, so we have here the, where is it, BA41050F. There it is, BA41050F. Oh, that wasn't the address that we jumped to, though, was it? It was right here, BA8E. This one here, BA8E, which is right here, BA8E, A4 30A. So it looks like actually some of that's been overwritten. And if we've got to the too bad. Now who's going to save Gotham Alfred? And the address we have in here, 61, in our instruction pointer, 6761, is down here, 67, 61, 6C, 66. Which seems to be what's causing us the problem here. We can't continue any further from that. Yeah, so it's basically given us an invalid memory address, I guess. So let's go x over 50x right here. Yeah, so whenever it tries to access that, that's not a valid memory address. Let's go back. Let's close this down for now, and let's just compare this with the shellcode option, with the shell craft.sh. And let's also, while we're doing this as well, have a look at the length of the payload. Let's print length payload and try to run this. I'm going to turn off the debug for now, actually. I'm going to go back. Actually, first let's compare the cat flag to this. I'm going to go info. .92 if we want to cat flag.txt. Oh, but it's going to be the same because we're doing offset minus length of shellcode there, right? Oh. Broken pipe. Oh, 549 it gave there as a size. Oh, ASM. Okay, so we need to assemble that into the raw bytes. And 92. So it's going to give the same because we're checking the length there. Let's go back a second. I'm interested to see what the actual length of the shellcode is. .48 using shellcraft. Using the sh, sorry. And with catflag.txt, it's 3 bytes shorter using catflag.txt. Okay, but neither of them are working anyway. So I'm gonna re-enable our other debug method. Let's take this out. Let's go and do the piebase debug method using the GDB script here. So I'll minimize this. We'll go back and we'll do Python exploit GDB no ASLR. It's set to break at the moment at, which was the offset? Let me just see what offset that is. Let's do R2 back computer AA AFL S. Is it just main? It's just set to let's have a look. PDF. Okay, set down at the leave here, which is, that's good. Yeah, that's kind of where I think we should have it. So let's try and run that. We'll move our Pwntools debug screen to the right, and then we'll move our GDB screen to the left, and we have our breakpoint set up as we should here, as we set the offset. So we can have a look now, and let's grab our, we don't have the leaked address yet, do we now? Okay, let's hit let's hit continue. And we've got to the breakpoint here, we have our stack address now. So we can say x over 50x and have a look what's in x over 50x. Have a look what's in the in this address. So it's put in our NOP instructions, and then we have our shellcode. After that, we have here, we're just about to leave, so if we have a look now at, let's do x over 50x of the RSP. So we have the RSP here, and what we want to try and do is go step through here as it goes through our shellcode and keep an eye on the RSP and see what happens to it. Let's go ni for the next instruction. It's going to go to return, so we'll do ni again, and we've got some nop instructions here. We could have a look at our stack again. Let's go through next instruction. Let's get through these nop instructions first of all, and get to our actual shellcode. Okay, we're starting to get there now. Next instruction where we're getting to this push instruction, and this is where we're actually getting to our shellcode here. It's a shame it's not showing the shellcode output on the right, the output here for us to look at and compare it to. But let's have a look at our. Let me just do x over 50x. We can see again our stack address, and we'll do x over 50x for our RSP. So if we look at the values we have here, we can see that this value here is right here. So this is where we wrote to on our stack, and we can see that our actual stack pointer as it's moving, this is where we've got to here. And so let's go next again, and we have this decrement, next. Let's try and have a look at our values again. Go through again, next instruction, and we can see that we're pushing. We'll run through that. And so the issue is here that each time one of these push operations occurs, it's actually getting to the point where it's overwriting some of our shellcode. And then by the time we get to, let's go next instruction. So now we've actually got to the point where it's crashed because, again, it's got this address in the RIP. So there's a couple of things we can do. We could look for some shorter shellcode to use. I did actually, I was struggling at this point, and I found a couple of people's solutions online. So one solution was to use a shorter shellcode, so we could get some shellcode from elsewhere rather than using our shellcraft here. Another option, which was really cool, which I saw from Pink Draconian on their walkthrough of this, was to use to grab a PopAD function. Let me do PopAD shellcraft. Oh. And let's grab this from here. And this will pop all of the registers on the stack, so we can go and have a look at the source as well. And it will pop. So the issue here, as things are getting pushed onto the stack, it's beginning to overwrite our shellcode. If we can inject some enough pop operations on there with our before our shellcode, then we can potentially ensure that there is still enough room. I just realized that the context level was set to info there. That's why I wasn't getting the any of the debug info here on the right. That makes sense now. Okay. Oh well, let's close that. We know what we're going to try and do here. I'll put that back to debug for now, and we want to use the shellcraft option then. So we're going to inject this before our. Let me put it here so we can switch to the shell if we need to, and we'll do shellcode equals. We need to do the ASM still. Shellcraft dot. I wish you could get autocomplete here. If anybody's got autocomplete working in VS Codium or VS Code, with shellcraft, please let me know, because it would be really handy just to be able to see what's available and highlight it and see what it actually does. It'd be cool. Alright, so this is going to pop values from the stack into all of the variables to counteract those pushes that we're dealing with. So let's add a plus equals here. So we're going to do this pop add, and then we're going to concatenate our shellcode, which is going to cat flag.txt, and then we're going to put enough nops to make it up to our stack address, which is going to be the return address, which is going to point to this stuff here. And hopefully, let's go back and try and run that. I'm going to try and run it first of all just without the debug. Let's just do Python exploit. Try to run that, and we get back our fake flag, so it did print that out for us. So that does work, that's really cool. Let me see if we can take Linux out of that and just do shellcraft.cat. Oh, if you spell shellcraft right, you might be able to. Yeah, you can. Alright, that's really cool. So if the context is set up here, you don't even need to worry about putting Linux or x64 or anything. We can just do shellcraft. And similarly then, if we go ahead and say instead of cat flag.txt, let's do the shell instead, and we'll run that, and we get end of file because we're waiting for a flag. But if we didn't want to wait for a flag, we could say io.interactive and give us a shell. Okay, what am I missing? I feel like that should be working. Let me set it back to Linux. Okay, I commented some of this code, which I'll be uploading to the GitHub, just as if by magic. Commented some of this and tried to run that again. We still get the end of file for a while. Okay. Oh, I didn't set this to even spawn a shell. Okay. That would help. Okay, yeah, there we go. Yeah, I'll put this script online, so you can change this between. I'll leave this here. You should be able to do it just without the Linux as well. Let's comment that out, and we'll do cat flag.txt. Let's save that. I'm going to comment out the spawn shell. Again, we wouldn't need this pop add, just pop all the registers, if we just used a shorter shellcode as well, which you could find online. So let me set this to info. Let's just run that, make sure it's all working fine. Yep, just got our fake flag back. So what we can do now is go to our HackTheBox. Let's start an instance. Might take up to a minute. Okay. Let's copy this and so we want to go Python exploit. We'll paste in the server address and the port number, take away that colon, try and run that, and we get back our local flag. Oh, I missed the remote. So we need to give it the remote flag. Try that again, and we get back the actual flag. Cool. We could run that with debug on as well. Let's go back to our option here. Let's set debug. Run that again. And you can get all the debugging info as it's going through. We get our flag again there. Or we could go back and let's leave it on info and let's change this to spawn a shell instead. We can change that to interactive instead of grabbing the flag. And then we can change this to shellcraft.sh instead of shellcraft.cat, And if we try to run that again on the remote server, here we can see that we've got into the directory. We've actually got a reverse shell as root, and we can then just cat out the flag from there. So both are fine options. And yeah, that's that. Aware that this video is now over 1 hour long, so I'll wrap it up here. Yeah, I'll put this script online. There'll be a link to it in the description. If anybody solved this differently, let me know. I was actually trying to play around with this to use, rather than using shellcraft, to go and use ropper, or well, we can import a rop, create a rop object here, say rop equals rop of the elf, and we can search for gadgets. And I was trying to find gadgets to accomplish the same goal as this pop ad, but I couldn't get anything working. This worked for me. The other option again was to use a shorter shellcode. But if anybody's watching this and they used a different method of creating space here, I'll be interested to know. You can let me know in the comments. You might be able to notice that I'm not an expert in binary exploitation. I'm learning as I go, and I think it helps me in the learning process to try and explain what's going on, and also it's hopefully useful for some people because I'm trying to explain it in a way that I would have explained it to myself shortly ago when I was trying to learn the same stuff. So yeah, hope you enjoyed the video, and any questions, comments, leave them down below. Thanks.